Hello and welcome to session 2. In session 1 we saw about the progress that we've made in the Fault2SHA laboratory so far and some of the work that's come out of that. We now want to look at fault data processing and hazard modeling and sharing fault data in general. So I'm going to invite first Ryan Gold to speak and then ask that Richard Styron is ready to speak after that. Now we go to Richard Styron, so if we could stop share your screen.
Okay. Yeah.
And then,
okay.
Brilliant. We're back. And if I can ask for Athanasos to be ready after Richard, thank you.
Okay. Okay, so it's on someone else's screen. Okay, great. Okay, hello everyone. Thanks for watching. I'd also like to thank my co-author Thomas Chartier and my colleagues at the GEM Hazard team. Today I'm going to present on integrated origin scale fault characterization, GEM's new fault model for China and beyond. Next. At GEM, now that we are finished with the first versions of the global mosaics, we are building new tools and new data sets to improve regional hazard models. The goal is to produce fault source models that are more realistic, accurate, and internally consistent than our previous efforts. Toward this end, we have 3 tools that are in development. Euler, which is an elastic block modeling program to resolve fault slip rates in a region through joint inversion of geologic and geodetic data. SHERIFS, which you've heard a lot about today, which is a tool to create probabilistic sub to multi-fault rupture collections based on fault network geometry, slip rates, and the shape of regional magnitude frequency distributions, and other OpenQuake tools including Hamlet, which is our package for statistical evaluations of seismic source models. The first use case for all of these tools together is a new hazard model of China being developed by GEM. It is also one of the largest and most complicated active fault systems in the world. So if we can make it work here, we should be able to make it work anywhere. Next. So the first step is to make a fault database that we can build off of. So here's a map of the faults in the blocks with line thicknesses for the faults proportional to the log scaled fault slip rates. To make this, we remapped China and the surroundings at a scale of about 1 to 100,000, based on my interpretations of both previous work such as Hamlet map, more recent publications, and available topographic and satellite imagery. This will probably be released as Hamlet map 2.0. We also made a regional block model simultaneously so that the faults in the blocks match up naturally. The block model infers 157 quaternary fault slip rates and over 3,000 GPS velocities to yield internally consistent slip rates on all 957 fault segments. The median residual velocity and or slip rate is 0.6 millimeters a year. So we have a very good fits. Next. So this is a movie, if you could play it. Just click, hopefully. Okay, so one of the best ways to visualize the results is to extrapolate the predicted instantaneous block motions backward and forward in time. So we just saw from 5 million years in the past to 5 million years in the future. Next. Okay, so the slip rates that we obtain with Euler are fed into SHERIFS to get rates of ruptures in the fault system. SHERIFS converts the slip rates on the faults to earthquake rates by defining a broad set of ruptures based on the fault network geometry and incrementally converting a small fraction of the slip rate of each fault into earthquake rates for each of the ruptures. Next. So here on the right, we can see examples of all the ruptures that cross a small segment of the Alten-Tog fault. So the SHERIFS takes 3 main inputs: the slip rates and 3D geometries of the faults, a target shape of the magnitude frequency distribution defined for the whole model. In the case of China, we use the B value observed in the earthquake catalog. In addition, since this model is very large, for some reasons, we use a local B value. We also need to define the set of ruptures that are possible on each fault in the system. We automatically build diverse sets of subfault to multi-fault ruptures based on parameters such as a regional maximum magnitude and a maximum distance spacing between ruptures. In addition, we consider that part of the seismicity does not occur on the faults, but in the surrounding background regions. Next. In a logic tree, we explore the uncertainties associated with each of these input hypotheses. SHERIFS is run for each combination of parameters. By comparing the modeled earthquake rates to the observed rates, we can select combinations of input parameters that most closely match the rates while converting most of the slip rate budget of the faults into the earthquake rates. This comparison is done at several levels of the fault system. Next. Once we have a rupture model from SHERIFS, we can evaluate the model's performance compared to the catalog using Hamlet, which is a programming we're developing in-house. This lets us break down models spatially and component-wise to test different aspects of the model's performance through statistical likelihood and physics-based metrics. Next. So to summarize, we're making a system to build large-scale fault source models that are more realistic, accurate, and internally consistent than we have been previously able to do. This happens through fault slip rates calculated with Euler that are internally consistent and use the maximum information available. Earthquake rates on sub to multi-fault ruptures calculated with SHERIFS that incorporates fault network geometry, individual fault slip rates, and regional magnitude frequency information. Quantitative evaluations of model performance that will let us tune the models and understand how epistemic uncertainty impacts the accuracy of earthquake forecasts. With this linked approach, we can more quickly and reliably build and update the models that make up the GEM hazard mosaic. Okay, next. So thank you, that's my last slide.
Thank you very much, Richard. And I now go to Aphanisos to ask you to make your presentation, and then we'll have some short time for questions.
Hello, everybody. Thanks for watching. This is a presentation of the NOAA Faults version 3.0 geospatial database of active faults in the broader area of Greece and Aegean. I'm making clear that I only present data here, not models. Next. So this is a comparison of the previous version of the database. Version 1 was first published in 2013 in blue. Version 2 2019 in green, which is mostly covered by red, which is the current 2020 version of the database. These are all active fault traces. Next. So the number now of faults that are included in this database is 2,475. Next. This is a table, the attribute table of the database showing how we proceeded with basic information about each active fault, like the length, kinematics, geological setting, location reliability, which is a function of the mapping scale of the original paper, the monitoring, paleoseismology, creep, co-seismic, slip data, activity reliability, that is, if it is proven active fault, likely possible, slip rate, instrumental seismicity, etc. And then we added deep direction, strike, deep angle, and rake on version 2.1. And then version 3.0, we added the references and the DOIs and compiler names. Next. This is the flow chart showing how we work. We select the scientific paper, we report in active faults, we select the figure, then we add the map in the GIS environment. We use ArcGIS Pro, we do georeference the map using all the appropriate georeferencing tools, and the errors associated are also recorded. We digitize the fault trace, we report also the errors, and then we fill the fields of the attribute table, etc. So this is classical GIS work taken with all precautions. Next. Some statistics reporting 2,334 normal faults for this area, which is expected because it's a well-known back arc region behind the Hellenic subduction. And also on the right, you see the variation of the magnitude of each fault, which is taken from the literature, from each paper. So we have 15 faults with magnitude over 7. This is moment magnitude, etc. Next. So we have reliable data on slip rates on 105 of these faults. And also we collected data on surface rupture and proximity of epicenters of strong earthquake events, the traces of active faults, that we allowed the identification of 95 seismic faults on this database. In our database, nearly 50% of the active faults imply high seismic risk in the broad area of Greece. Next. This is a variation of the slip rate data we have. So we see here that almost 60 faults have slip rates below 1 millimeter per year. Next. This is a very easy to use web GIS application. What you see here is the seismicity that has been recorded in the last 24 hours on top of the faults. These data are from the National Observatory of Athens seismic analysis room. Next. If you log into this web address on the lower left, you enter your database, and then you can click on each of these lines. You end up with the attribute table with all the data we have, plus a figure. If a figure, I mean a field photo, if this is available. Next one. For example, we have on the left, you see field trace, a fault trace, and a field photograph of the Tyrnavos fault in North Thessaly in Greece. The footwall is on the left, handy wall on the right. And this building there is a Paleoseismological Museum that was founded about 10 years ago by Ricardo Caputo. On the right, you see the same information, the pop-up window, the Tyrnavos fault that appears on the Noah faults version 3. And there are all the fields.
30 seconds left, thank you.
Sorry, okay, very quickly, next one, please. And again, some data that is available, like strong earthquakes, aftershocks, GNSS network. Next one. And all the layers are here. There are 21 layers on this database. Users can overlay, can see things like slab top, slab model, etc. Next one. The usage of the NEA faults, very, very nice a lot of users. Like the last week, for example, we had the Samos earthquake. We had 127 hits. Next one. And the last year was about 1,677 views of this database. I mean, users, they use the data. Next one. And that's all. Thank you very much.
Thank you very much, Stefanos.